So yesterday we talked about Stokes shift at quite a great length, and also explained this some of these processes from this well-known Jablonski diagram. So I will also do a little bit of recap what we discussed yesterday, and then move on to more specific aspects of environment sensitivity using fluorescence. Okay, so what we discussed yesterday was that you have got a ground singlet state, okay, typically denoted as S naught. They're also associated, each of this electronic state are also associated with vibrational states, okay, which are much lower in energy compared to, of course, the electronic transition. And we also discussed that absorption, of photon excites this from S0 to S1, sometimes to S2, S3, depending on where you excite. Of course, if you go to a shorter wavelength, then of course you can get the molecule excited to higher electronic states. But fluorescence typically occurs from the lowest higher electronic state. Okay. And of course, there are selection rules that govern the transition, which transition will be more probable. In the vast majority of cases, S0 to S1 transition is highly probable. However, there are fluorophores where S0 to S1 is not completely allowed. It is rather a forbidden transition. So whereas S0 to S2 might be more allowed transition, then of course you excite the fluorophore at the bluer end of the absorption spectrum to excite that. That'll allow the molecule to absorb more photons, okay? And of course, after excitation, we have got a vibrational relaxation step. This is vibrational relaxation step. And then, of course, this can get further stabilized by what we discussed yesterday as solvent relaxation. And this essentially is a dipolar relaxation because at the excited state, you've created a transient dipole moment, which is much higher compared to the ground electronic state. Therefore, water molecules or solvent molecules or other dipolar medium, whatever you have, so molecules are going to sort of try and relax the instantaneously created dipole, and then of course you will see emission, photon emission, which is basically fluorescence, right? So just to again remind you, absorption is on the femtosecond time scale typically. Vibrational relaxation is on the picosecond time scales. So is the time scale for solvent relaxation, picoseconds. But depending on the solvent mobility, okay, for instance, viscosity is actually a good marker of viscosity. The solvent relaxation can get slowed down to hundreds of picoseconds, okay, sometimes. So that then, of course, you see certain interesting features in fluorescence emission, which if we have time, we'll talk about it. So you can, have slower solvent relaxation particularly in biological systems, highly organized systems like in micelles, reverse micelles, membranes, protein aggregates, uh, higher supramolecular complexes, so you can have much slower solvent relaxation. But typically from, let's say, 1 to 10 picoseconds is typical solvent relaxation combined with vibration relaxation. And of course, vibration relaxation typically uh, is faster than the solvent relaxation. And fluorescence, of course, occurs typically on the nanosecond time scale. And of course, it can be, depending on fluorescence lifetime, it can be, it can vary, okay? And of course, the probability of transition, there are a lot of other things involved here, but typically nanoseconds. So they are very well separated, 10 to the power minus 15 seconds, 10 to the power minus 12, 10 to the power minus 9 seconds. Okay, so they are kind of quite well, the time scales are quite well separated. And of course, that's one of the reasons why fluorescence becomes so useful, because typically in absorption spectroscopy, you don't see very clear solvent dependence or the environment dependence. And of course, there are dyes which can give you some information about the dielectric constant of, it varies with the dielectric constant of the medium, but those are very special dyes, right? Whereas fluorescence is typically way more sensitive because the time scales are so well separated. You can have this solvent relaxation intermediate step before fluorescence emission occurs. Therefore, you can observe what we termed as fluorescence Stokes shift. Okay, so this is in lambda nanometer. Okay, let's say this is my absorption spectrum. This is fluorescence spectrum. And of course, I mean, if you normalize this some way absorbance and fluorescence, and you see a typical shift, which is ascribed to both vibrational and solvent relaxation. And if you have more solvent relaxation, of course, there'll be more shift. And sorry, I also discussed yesterday that more solvent relaxation at the excited state also is evident by much lower fluorescence, because if you look at this step, or just look at this S1 to S0 step, okay? Okay, this is essentially fluorescence, right? And you can sort of think about this as a reaction, okay? It's sort of like a first order chemical reaction, okay? You can use the chemical kinetics approach to sort of quantify the rate of this process, right? You can imagine that it's like, sorry, the reactant and product. So S1 to S0 is a two-step, okay? First order reaction. And therefore, you have a rate constant associated with it, which is basically rate of fluorescence, right? Which is typically, let's say, okay, rate of fluorescence is, let's say, K, and fluorescence lifetime, okay? The lifetime is essentially how long S1 is living before its transition to S0. So fluorescence lifetime is inverse of, not proportional, inverse of rate constant, okay? So this is fluorescence lifetime, tau is fluorescence lifetime. okay? And K is basically the rate constant, okay, of fluorescence. And there is, of course, a first order reaction will be having a unit of second inverse or per second. And of course, this is in seconds or nanoseconds, okay? So this is in seconds unit, this is in per second unit, okay? Sorry. So fluorescence lifetime essentially is the inverse of the rate. I mean, this is true for any process, right? I mean, the lifetime, the time constant is inverse of the rate constant, right? And of course, when we talk about K, K, of course, you can denote or describe K as, of course, Kr, which is the radiative rate constant, plus Knr, okay, non-radiative processes. Notice this is a rate constant, so I'm denoting this using a small k, okay? So capital K is typically used for equilibrium constant, a small k is used for a rate constant, okay? So K essentially is, there are two types of processes. One, of course, is radiative process, which is what you see here as fluorescence. And there is also non-radiative process, or a collection of non-radiative processes, which can bring the fluorescence excited state down to the ground state without emitting a photon. And that can happen in a very facile way if dipolar solvent molecules collide with the excited state and basically dissipate its energy, okay, through thermal dissipation. So as you can imagine, the fluorophore which undergoes extensive Stokes shift, other fluorophores will also have more non-radiative decay channels, therefore faster K, because you've got now quite a significant contribution of K and R, therefore shorter lifetime, because if K is higher, fluorescence lifetime becomes shorter. And radiative lifetime, of course, is a theoretical lifetime, okay? Kr equals 1 over tau R, which is basically radiative lifetime, which is a characteristic lifetime of a fluorophore if you don't have any other non-radiative decay channels, okay? So if you, but in practice, you don't measure tau R, you measure tau, which is basically much lower than tau R, okay? Because you have now got K and R. And of course, there are multiple non-radiative processes. Therefore, you can also have a sigma, so summation of many of these K and R's. Okay, there might be other rate constants. So rate constants are additive, but of course, lifetime is inverse of rate constants. They are not additive, right? So so basically, fluorescence, the sensitivity of fluorescence, so much of usefulness of fluorescence actually comes from non-radiative decay channels, right? Because if there was no non-radiative decay, then of course you will not be able to sense the immediate environment, right? So it's interesting to state that it's a non-radiative process or collection of non-radiative processes basically dictate the unique ability in fluorescence to capture unique environment and so on. Okay, so KNR, of course, is in some way related to solvent relaxation, as I have already mentioned, that if you have a hydrocarbon solvent or hydrophobic environment, KNR will be minimal. Therefore, K will be close to KR. Okay, therefore, tau, the lifetime, is going to be very close to the theoretical calculated lifetime or radiative lifetime. Okay, so basically by monitoring either fluorescence intensity or fluorescence lifetime, you will be able to make some assessment of the immediate environment of the fluorophore. Okay, and also you can imagine from here, if we now start talking about the efficiency of fluorescence, which is quantified using quantum yield. Okay, let's say Q. Okay, it's also in some places denoted as phi, I think. So quantum yield, essentially, as I have discussed yesterday, is the yield of photons, fluorescence photons, over the photons that are absorbed. Okay, therefore, this is going to be related to KR plus KNR, okay, over KR, right? So because this is now K, okay, in other words, K by KR, okay. So this is radiative rate constant, and sorry. So I think there was some issue here. So basically, the quantum yield is going to be, of course, ratio of K, the total rate constant over, KR over KR plus KNR. Okay. So this is essentially KR over K, total K, okay, which is essentially tau by tau R, okay. Let's say a theoretical lifetime of a probe is, let's say, 10 nanoseconds, and you see observed lifetime is 3 nanoseconds, okay. Then, of course, quantum yield is going to be 0.3 because it is decaying faster than it is supposed to because of additional KNR, which is bringing, of course, the lifetime down to 3 nanoseconds. So it is much shorter lived compared to the lifetime which one would observe, let's say, in vacuum. Okay, in vacuum, of course, you'll have no solvation. Therefore, the lifetime will be at its longest lifetime. You'll be theoretical lifetime you'll be able to observe. And of course, experimental analogous to vacuum is, of course, hydrocarbon solvent, right? Because there is no, so hydrocarbon is not dipolar. Therefore, you are not going to see extensive dipolar relaxation, which you see here, okay? Therefore, quantum yield is also related to the ratio of lifetime and theoretical lifetime. Okay, so in other words, in the presence of solvent relaxation, okay, your fluorescence becomes less efficient, and of course, depending on the solvent or the environment quality, you can see either longer lifetime or shorter lifetime, less fluorescence, more fluorescence, coupled with Stokes shift. So these are all going to go hand in hand. That lifetime, fluorescence intensity, and Stokes shift. So what I mean by hand in hand, so so let's say I've got different solvents, okay? So this is fluorescence intensity, this is, let's say, wavelength in nanometer, okay? So as you change the polarity, okay, or dielectric constant, okay. As you know, water has dielectric constant of 80, whereas hydrocarbon can have dielectric constant of 20 or even lower, 10. Okay, so let's say in water, or let's say dimethyl formamide, which is also very polar, organic but polar solvent, or DMSO, highly polar but it's still organic. But dimethyl formamide is even more polar compared to DMSO. Let's say if I plot the fluorescence in spectra, let's say if I had to look at the spectra in different solvents, this is how it'll look like. And of course, in water, you'll see much weaker fluorescence like this. In let's say dimethyl formamide, you'll probably see a bit stronger, but much less Stokes shifted. Let's say, propanol, okay. Let's say, even more non-polar solvent. And let's say if you have hydrocarbon, then of course you're going to see even higher fluorescence intensity, right? Because your quantum yield is going to be higher, okay? This is highly polar or dipolar, because highly polar solvent molecules are going to impart more dipolar relaxation or solvent relaxation. Let's say this is water, okay, and this is hexane or hydrocarbon, let's say. Okay, so this is non-polar, okay. So what you're going to see, Stokes shift is going to be the largest in highly polar, that is associated with much weaker fluorescence, because much of the decay happens through KNR, okay, non-radiative decay. And of course, KR is, the observed rate is basically the summation of different rate constants, okay? Therefore, you're going to see much smaller fluorescence quantum yield, because your quantum yield is essentially the ratio of this, and also this could also be denoted as tau over tau r. So fluorescence lifetime here is going to be tau, let's say, short or fast decay, and here tau is going to be long, okay? In other words, slower decay. It will almost be as slow as the vacuum or theoretical lifetime, okay? And here you have more solvent relaxation. Therefore, there is a huge Stokes shift, okay? Compared to, let's say, excitation is somewhere here. Of course, here, let's see your absorption peak. And the little bit of Stokes shift you see here because of vibrational relaxation. And then, of course, due to different solvent relaxation, you see different extent of Stokes shift. In fact, there is also a relationship between the dielectric constant and the fluorescence Stokes shift. You can even quantify that. And of course, this is more physical chemistry or photophysics, you can say. But of course, the application for our purpose, we are interested in biological application, right? And of course, in biology, we are not going to talk about different solvents or organic solvents, but we are definitely interested in a unique environment of that particular fluorophore. And I already mentioned yesterday that, if you, let's say, have got one, example is, let's say, you have got an unfolded protein, okay? And let's say you're studying protein folding. Often it's easy to, give example from protein folding. And of course, that can also, can also give examples from membranes and so on. We'll talk about some of these examples at some point. Let's say this is an unfolded protein. You've got a fluorophore here, which is, let's say, tryptophan. And here, let's say you have a folded protein, okay? Okay, and here, fluorescent dye or tryptophan is, let's say, exposed to water, and here it's buried in the hydrophobic pocket or hydrophobic core of the protein, okay? So let's say this is folded protein. This is unfolded protein. Okay, let's say you are interested in studying protein unfolding or refolding, okay? So now you can use basically the same conceptual framework to sort of characterize that, the tryptophan is exposed out to aqueous medium, and you have much lower fluorescence intensity, much larger Stokes shift, and much smaller fluorescence intensity, coupled with the lower quantum yield and shorter lifetime. Okay, whereas in the folded form, where the protein essentially is buried in the hydrophobic pocket, you are going to see much higher fluorescence intensity, higher quantum yield, longer fluorescence lifetime, and of course, much smaller fluorescence Stokes shift. Okay. And of course, if you are studying the folding process kinetically or in an equilibrium manner, you should be able to, sort of go from one end of the solvent quality to the other end of the solvent quality. Okay. And I would also like to add here that interior of the protein is not really like hydrocarbon. This is more like, I would say organic solvent, because if you think about the interior of the protein, of course, you can have lots of side chains, hydrophobic side chains from, isoleucine, leucine, valence, and so forth. You also have got lots of amide bonds, the backbone amide bonds. Therefore, the interior is never going to be like hydrocarbon, right? It is going to be a little bit polar than hydrocarbon, okay, if you think about the interior of the protein. Then you can ask the question, what is basically the dipolar medium in a folded protein where, let's say, tryptophan is buried in the core of the protein. Of course, you can see there is some limited solvent accessibility. So there is probably a little bit water can also penetrate, but if it is a deeper hydrophobic pocket, of course, it will be almost completely solvent excluded, water excluded. Therefore, in that case, the dipolar medium can become, amide bonds because CONH being a little bit polar, you have dipole moments. It is going to act as solvent within the protein molecule. But if the protein is very well folded, there is very little dynamics of polypeptide chain within the folded core of the protein, then you of course don't expect much dynamics that is required to relax the excited state. Of course, because of the dynamics is frozen or slowed down considerably in the folded protein, you don't see much solvent relaxation even from the protein matrix. Okay. Therefore, this is by looking at just simple fluorescence spectrum, you will be able to make you will be able to characterize some of this, folded and unfolded states and their intermediates of folding and unfolding by just looking at the characteristics of tryptophan fluorescence. Okay. This is one of the examples. There are other examples like let's say membrane. If you have a fluorophore embedded deeper into the membrane, then of course you're going to see similar. Then of course it becomes more like hydrocarbon environment. So if you're familiar with lipid bilayer, and I'm sure all of you are familiar with lipid bilayer. Okay, I'm just drawing only a part of it. If you look at, let's say, this section of the bilayer, so these are, let's say, polar head group. Let's say you have POPC, okay? Then, of course, this is a polar head group. And let's say you have got a fluorescent dye, depending on the polarity. If the fluorophore is light here, then, of course, it's going to sense the hydrocarbon environment around it, because the long chain fatty acids that are required to constitute the lipid molecules will basically impart hydrocarbon environment around it. Whereas if fluorophore is somewhere here, then of course there is some water penetration. Therefore, here you will see mixed, aqueous organic behavior. And of course, by looking at the fluorescence behavior, you will be able to make assessment where that particular fluorophore is located in the membrane, in the lipid membrane. Okay. So sometimes, people also use labeled lipids to do some very fascinating, membrane structural studies, which we will talk about much later during the course. So, so what I, mentioned from the Jablonski diagram, a little bit, just a little bit of, a chemical kinetics treatment, mathematical treatment, very little. Of course, one can expand these things in a typical, photophysics course, but of course, since this course is targeted to biologists, so I'm sort of trying to minimize the, so only the essential equations I'm going to show. So Jablonski diagram is the central diagram in fluorescence spectroscopy. Therefore, I would like all of you to make yourself familiar with this, because many of these things can be explained by just looking at simple Jablonski diagram. Okay, so if you interpret the fluorescence spectral position like the Stokes shift, and of course Stokes shift is typically determined by, as I said, Stokes shift, okay, is basically del lambda, okay? It's lambda emission max minus lambda absorption max, okay? Whereas alternatively, you can also just look at the peak position, okay? Peak position is going to have, red shifted, okay? This is red shift. And of course, if you fold the protein, we're expected to see a blue shift, right? So red shift and blue shift. And of course, concomitantly, you will also see the increase in fluorescence and of course, slowing down in fluorescence decay, so you'll have longer lifetime. Sometimes this is, there are exceptions, which we'll talk about later when we talk about tryptophan fluorescence and applications in protein folding later. Now, another question I'd like to ask here, that if you are using, so here essentially you're using aqueous medium or the, or whatever solution, buffer solution you have to basically, that is, water is going to quench the fluorescence by collisional quenching, by making non-radiative decay process much more facile, and therefore and of course in the hydrophobic region, non-radiative decay channels are shut off. Therefore, you see much higher fluorescence, longer lifetime, more quantum yield, and so forth. Now, you can also validate this by doing some another interesting set of experiments, okay, by using what is known as quenchers. Okay, so you can use bona fide quenchers that can quench fluorescence. And if you're using water-soluble quenchers, then of course you are essentially monitoring how much water is able to penetrate down to the fluorophore, especially, let's say, in the folded protein. In the unfolded protein, it's all exposed out to, bulk water. Therefore, if you use a quencher basically is, there are different types of quenchers, okay? And we will spend some, time to sort of think about, what kind of quenchers are good for studies. And of course, this is also important for, imaging experiments. You need to have buffer composition where you don't have quencher, otherwise fluorescence will be highly quenched and you will not see in your microscopy imaging, or you'll see a very dim image, right? So there are various kinds of quenchers. One of the quencher, of course, is potassium iodide, in other words, iodide, okay? So iodide being a very, sort of heavy atom or ion in this particular case, So there is, of course, interaction between the fluorophore, excited state of the fluorophore and iodide. And there is, of course, this NR becomes even more facile because iodide is going to sort of collide with the excited state and brings the excited state down to the ground state. Okay, and this is much more specific quencher rather than water, which is basically is going to collide, and there is thermal dissipation because of collation. Here there is specific interaction of iodide with the excited state S1, and then there is, of course, shutting off of fluorescence through a multitude of mechanisms involving spin orbit coupling, photoinduced electron transfers, and so on. Okay, so you can have different kinds of quenchers. You can have heavy atoms quencher, for instance. You can also have some aromatic molecules which will accept electron, and then of course if electron goes to the quencher, then it's fluorescence is shut off. And then you can also have FRET, fluorescence or Foster's resonance energy transfer. That's also a special quenching mechanism by which energy is transferred from the fluorophore called as donor to the quencher called acceptor. Okay, therefore you can have different kinds of quenching mechanisms, and that allow you to sort of probe the region of biomolecules or region of biomolecular assemblies much more precisely. For instance, if you add potassium iodide, sorry, in tens and hundreds of millimolar concentration, which is huge, and then of course iodide is going to quench unfolded protein tryptophan located in the unfolded protein much more efficiently compared to the folded protein, because iodide can only go close to the fluorophore if water goes there, because it's a water soluble quencher. It basically, wherever water traverses, iodide also traverses, right? So iodide cannot just access the fluorophore if water doesn't go into the hydrophobic pocket of this protein. Therefore, by looking at fluorescence quenching efficiency as well, you will be able to sort of make some quantitative assessment, very dynamic assessment, which I'm going to talk about tomorrow and also next week. I want to spend a little bit more time in quenching because this is really fundamental in not just in studying some of these things, but also to be aware of the possibility of fluorescence quenching from various other sources, other reagents that people normally use without being aware that they can actually quench fluorescence. Okay. Therefore, fluorescence quenching is also very important. In fact, oxygen also quenches fluorescence. Oxygen is paramagnetic, so it can quench fluorescence through triplet state interactions. Therefore, if you degas the solution by doing using some method called freeze pump thaw, freeze thaw cycle, if you degas or if you purge the buffer with, let's say, nitrogen or argon, then of course your fluorescence lifetime goes up. It goes up, almost close to theoretical lifetime, because oxygen can also quench fluorescence. Okay, but quenching by oxygen is less severe for fluorescence compared to phosphorescence. And tomorrow I will also talk a little bit about triplet state intersystem crossing, and phosphorescence. Although phosphorescence is very interesting, but it has much more limited application in biology. Therefore, I will not spend too much time on phosphorescence, but I will definitely introduce and also tell you about phosphorescence. And also I'll mention in which cases phosphorescence might become important to study. All right, so I would like to stop here today. And if you have more questions, please feel free to ask me.